Welcome back to Maths with Mrs. J. I'm now going to start a series of videos where I'm going to talk about limits and continuity. They go hand in hand, they're not the same thing, but quite often it's a good idea to discuss them together. I'm going to go largely from a visual perspective, from a graphical perspective, because I find that that really helps people understand what's happening, particularly when you're taking limits from below and from above. I'm also going to point out here that I'm not going into university level understanding of limits and continuity. I'm sticking with the high school level, year 11 and 12 understanding. So we're largely going to start with the graphical representation and get an understanding of what continuity means and limits from a graph. And then of course we will go into some algebraic methods further down the track. Just having a look at these three graphs that we have on our first page, all three of these are continuous. One way of telling whether they're continuous or not, you could, in theory, draw the whole thing each time without having to pick your pen or pencil off the page. There are no jumps, no gaps, no holes, all right? This function is an interesting one here. You would not be able to differentiate that there because you wouldn't be able to get the tangent. However, it is still continuous. Let's have a look at some other examples. All right, in this case, we have two examples where we have discontinuities. The first function is discontinuous at x equals 0, and we can see that this must have been a piecewise function where we have a value when x is 0 and the value of the function is 3. When x is less than 0, we have this straight line coming up here right up to but not including y equals 4. And then above x equals 0, we have this parabola that begins just after the 8. We have jumps and bumps there. That is definitely discontinuous. This graph has 2 points of discontinuity. Here we have an obvious jump when x is -5, and here we have another issue of discontinuity when x is 6. This is actually a very interesting one that we will be looking at together when we're talking about limits. This is one of the unusual cases where the limit of the function is not the same as the value of the function. So it's kind of cool in that way. Let's proceed and look at some more examples. So yet again, we have another example where we have a function that would have been defined piecewise. We have something that looks like a cubic kind of situation to the left here. Then we have a very big jump down to what looks like another type of cubic. And at this particular value here, we have a hole in the function, and the actual value when x is 3, we're told is -1. This has 2 x values, so x is -2 and x is 3, where there are discontinuities. We will be having another look at this graph at a later stage to talk about limits. Having a look at these two graphs, well, these both have a discontinuity as well. Here, when x is 8, we have a hole in the graph here. We have a point where that particular function is not defined. However, we're told that when x is 8, f of x is 8. But this particular point here is not part of the function. That is a hole in the function and also a jump. Here we just have a hole in the function. For some reason, we don't know why. That particular curve is not defined when x is -4. That is a discontinuity. There is a break in the line, so to speak. Let's have a look at some more. We will be looking at all of these again later as far as limits are concerned. These ones are very obvious discontinuities. Certainly if you have asymptotes and you're heading towards infinity, even though you're heading towards infinity from both sides, clearly you're not going to touch, are you? You have to lift your pen up before you draw the next section of the graph. So that is obviously discontinuous at x equals 1. This one is also discontinuous, but where x is 4. Here we have some more piecewise functions. Very obvious jump here. It's discontinuous when x is 2. This one, although it is piecewise, is continuous. And you can check that by looking at the value x equals -2 and subbing into both potential values there, and it will actually be the same value. Same thing where the rule changes at x equals 2, the value will be the same. So there are no jumps there. That is actually a continuous function. And last ones I wanted to look at, some more discontinuous functions. This one's kind of cool because we have negative absolute value. So obviously absolute value would normally look like that, but we're doing the mirror image about the y-axis. 4 minus x squared is an upside down parabola that's been moved up to 4. 2 points of discontinuity there when x is -4 and when x is 0. This one here, we have a discontinuity when x is -2. So basically a continuous function is one where there are no jumps, no bumps, no gaps, no holes, where basically it continues on, funnily enough. That's why it's called continuous. In my next video, I'm going to start talking about limits from a graphical perspective, and we're going to have another look at all of these graphs from a limit perspective and see what's happening where there are those jumps and bumps.